Hi, thank you for having me. My name's Harry Marshall. I'm an assistant professor of radiology at the University of Western Ontario, and I'm thrilled to be talking at the first Canadian Siemens Innovation Think Tank. Today I'll be talking to you about AI in medical imaging. First, I'd like to give you a 50,000-foot overview about why I'm excited about this field. And what it really comes down to is that radiology is an enormous area of study, involving multiple subspecialties, several of which are shown here. So it shouldn't come as a surprise to you that no single radiologist knows everything. In fact, any individual really only knows a small piece of the pie. However, our collective knowledge is vast. I see AI as a mechanism to distribute that collective knowledge to the individual at the point of care. In other words, I see AI as a rising tide, where the boats being lifted are individual radiologists. Put in a slightly more technical way, imagine you have three different radiologists, A, B, and C, all performing the same diagnostic task. We could construct ROC curves for these radiologists, and you can see that A doesn't perform as well as B, who in turn doesn't perform as well as C. Now imagine we develop a machine learning algorithm called AI Prime, which performs better than radiologists A and B, but not quite as well as C. If we disseminate that algorithm to all the radiologists, it effectively pushes the histogram of areas under the curve up towards 1, skewing it to the right. As that algorithm gets better and better towards a theoretical perfect classifier, AI double prime, so too does the skewness of the area under the curve histogram towards 1. AI can do this a number of different ways, one of which is detecting subtle abnormalities that we might otherwise miss. The second is through providing expert interpretation of imaging findings. And perhaps the most exciting is interpreting images beyond human capabilities, unlocking data that might be invisible to our eyes. With that overview in place, I'd like to give you three challenges with respect to AI in medical imaging, two of which have to do with the digital hospital of the future, and one with imaging difficult patients. So let's start with clinical integration. Radiologists, like most people, are creatures of habit. We have our PACS systems with which we view medical images, we have our dictation software with which we generate reports, and we have lists that are often quite long, full of studies that we have to get through in any given day. And we have become pretty efficient at doing so. There is therefore a great deal of inertia from deviating away from our current practice, no matter how useful the change potentially is, because inevitably at first it will slow us down. That is why AI has to be made as easy as possible for the end user, because otherwise it will be difficult to achieve widespread adoption. So for example, how is a radiologist to know about potentially useful algorithms that might be applicable in their practice amongst a sea of algorithms out there from a number of different vendors? How are we to know that they have been properly vetted so that their performance has been characterized as actually useful? How are we to purchase these things? Is there an app store model? Do we buy them in bulk? Do you deal with individual vendors or sort of wholesalers? And finally, how can these be integrated into our PACS systems such that it doesn't disrupt our current workflow, but rather augments it? The hard truth is that no matter how useful an algorithm is, if these problems aren't addressed, it will simply not be used. A second challenge has to do with the data used to generate these algorithms in the first place. I would consider most medical data loosely structured. So for example, in radiology, we have DICOM files which house the medical images and a bunch of metadata. We have radiology reports, which are text. And then we have the patient record, which has a number of data types from highly structured, like laboratory values, to free text, essentially. This is useful for individual patients, but it's not very good for acquiring large data sets required to train machine learning algorithms. What's more useful from that perspective is to have labeled or annotated data. So as an example, in the bottom left, we have a CT scan, which has been segmented. All the individual organs have been colored in. That's obviously very labor-intensive, but is data-rich information. It doesn't have to be that complicated, though. The CT scan could just be have a digital label applied of the diagnosis, for example, appendicitis, or the imaging findings. If these digital labels are applied to all patients, then it becomes much easier to search for groups of patients that are similar to one another to feed in to the training sets of machine learning algorithms. In other words, I think that the organizational infrastructure of data in hospitals has to be completely revamped and shifted from an individual patient focus to an aggregate patient population focus, which would then facilitate machine learning research. The final challenge deals with the fact that patients tend to move around. Here you see an example of a restrained patient. He might be restrained for any number of reasons. He might be mentally ill, he might be intoxicated, he might be combative, he might be confused. But this isn't the only reason that patients move. They also breathe, they cough, they sneeze, etc. Now, normally this isn't really a problem, but it is if they are currently getting a scan. On the left, you can see what an MR of the liver looks like if a patient breathes throughout the acquisition. And on the right, you have the CT scan of the head as the patient rotates their head during the scan. As you can see, it can essentially render the images non-diagnostic. I think AI will play a role in attenuating this problem. This is a simplified slide, but it kind of gets the idea across. In the top left, we have fully sampled, uncorrupted data acquired by, in this case, the MRI. You can then use that data to create a very nice image through any number of reconstruction methods. In the bottom left, you have either undersampled data, implying that it was acquired faster and therefore limiting the amount of motion that occurred during the acquisition, or data that's actually corrupted by motion artifact. The idea is to take the good image generated by fully sampled data and pair it with the undersampled or corrupted data in order to train a neural network to generate nice images from lower quality data. I hope that these challenges have given you a little food for thought and some inspiration of directions you could take going forward, and enjoy the rest of the ITT. Thank you so much.